40 light-years away, 7 planets orbit a dim red star. And after years of calling them our best hope for finding life, JWST just made astronomers quietly delete their own research. So let us start with why everyone was so obsessed with TRAPPIST-1 in the first place. Because if you are new here, this background is going to make the twist so much more satisfying. Back in 2017, the announcement hit like a thunderbolt. NASA held a press conference that had the entire internet speculating for days beforehand, and when the news finally dropped, it delivered. 7 rocky planets, all roughly Earth-sized, orbiting a small red dwarf star called TRAPPIST-1. 3 of those planets sitting comfortably within what astronomers call the habitable zone, that sweet spot where liquid water could theoretically exist on a planetary surface. For the first time, we were not just talking about one potentially habitable world around a nearby star. We were talking about 3. And they were close enough that a telescope like JWST could actually study them in serious detail. The scientific community went absolutely electric with excitement. Headlines everywhere talked about alien life, second Earths, and humanity's greatest discovery. Even the cautious scientists who normally resist hype were choosing their words very carefully, which in astronomy speak basically means they were thrilled. The reason TRAPPIST-1 felt so promising came down to a few key factors. First, red dwarf stars make up the vast majority of stars in our galaxy. If planets around them could support life, then life-friendly environments might be incredibly common throughout the cosmos. Second, because red dwarfs are so small and dim, their habitable zones sit much closer to the star, making transits, those moments when a planet passes in front of the star, happen far more frequently and be much easier to detect and study. This is exactly what JWST was built for. Studying atmospheres by watching starlight filter through them during those transits. Scientists could finally get answers to questions that had been building for nearly a decade. Do these planets have atmospheres? What are those atmospheres made of? Could any of them actually support life? Here is where things get complicated, and where the story takes its first major unexpected turn. JWST started looking at the innermost planets in the system first, specifically TRAPPIST-1b and TRAPPIST-1c. These 2 planets orbit very close to the star and were never considered prime candidates for life. They are too hot, baked by stellar radiation. But studying them was supposed to help scientists build a baseline understanding of the system before moving outward to the more exciting habitable zone worlds. What they found on TRAPPIST-1b was already a warning sign. When astronomers measured the heat being radiated from the planet's day side, the numbers suggested something that barely anyone expected. The planet appears to have little to no atmosphere at all. A bare, rocky surface with almost nothing to hold heat or distribute energy. Not a Venus-like thick atmosphere, not a thin Mars-like one. Essentially nothing. The kind of world that would make survival for any life form essentially impossible. Then came TRAPPIST-1c, and the results were equally stark. Despite being slightly farther from the star and sitting in a position where some scientists thought a thick carbon dioxide atmosphere might have survived, the thermal emission measurements came back and told a very different story. The planet is too cold on its night side relative to what even a modest atmosphere would allow. Again, the data pointed toward a world with at most an extremely thin atmosphere. Nothing substantial enough to regulate temperature in any meaningful way. Now let me pause here for a second because you might be thinking, okay, the inner planets have no atmospheres. That makes sense. They are close to a violent star. What did you expect? And that is a reasonable reaction. But here is why this matters so much more than it sounds. Red dwarf stars like TRAPPIST-1 are not just small versions of our sun. They are fundamentally different in character. They are far more active in their early lives, erupting with massive stellar flares that blast out enormous amounts of ultraviolet and X-ray radiation. This radiation is absolutely savage when it comes to planetary atmospheres. The concern among scientists was always that the TRAPPIST-1 planets, because they orbit so close to the star even in the habitable zone, would have been bombarded by this radiation for billions of years. The question was, whether their atmospheres could survive that kind of punishment. What JWST is telling us now is that for the innermost worlds, the answer appears to be no. The radiation won. The atmospheres were stripped away. And the deeper worry, the one that nobody wants to say too loudly but everyone is thinking, is that if the inner planets lost their atmospheres, what does that tell us about the habitable zone planets further out? This is where the tension really starts to build. TRAPPIST-1, F, and G are the 3 planets sitting in the habitable zone. They are the reason the whole system became famous. They are the worlds where scientists dared to dream about liquid oceans, about biological chemistry, about the possibility of life. And JWST has begun studying them. The data is still accumulating, the observations are still being analyzed, and the full picture is not yet complete. But what researchers have gathered so far is already challenging the optimistic scenarios that dominated scientific thinking just a few years ago. The situation with atmospheric survival around TRAPPIST-1 is far more uncertain than scientists initially hoped. The stellar environment, even for the habitable zone worlds, is intensely hostile. These planets are likely tidally locked to their star, meaning one side always faces the star in permanent daylight and the other side sits in permanent darkness. That alone creates extreme temperature gradients that would challenge any atmosphere. Add the ongoing stellar flare activity, and you have an environment that would require some very specific planetary chemistry to support a protective atmosphere over geological timescales. Some researchers have proposed that volcanic outgassing could replenish atmospheres that get partially stripped. If a planet's interior is geologically active enough, it might continuously pump gases back into the atmosphere fast enough to keep it viable. Others have suggested that the planets might have started with such enormous amounts of water that even after significant atmospheric loss, enough remained to create at least shallow oceans. These are still live possibilities. The data does not completely rule them out. But the confidence level that was once attached to TRAPPIST-1 as a promising target for life has unquestionably dropped. And here is where the story takes yet another unexpected turn. Because while one door seems to be closing, an entirely different and equally fascinating one has started to crack open. The very strangeness of what JWST is finding is teaching scientists things about planetary science that are genuinely new. Every time a planet defies expectations, it forces researchers to dig deeper into the physics, to question their atmospheric models, to test their theories about stellar radiation and planetary formation in ways that refine our understanding of worlds across the entire galaxy. TRAPPIST-1 has become something like a natural laboratory. Not necessarily the life-hunting paradise some imagined, but something arguably just as scientifically valuable. A place where the rules of planetary science are being stress-tested at the cutting edge. The measurements of thermal emission from TRAPPIST-1b and TRAPPIST-1c required extraordinary precision. We are talking about detecting temperature differences of just a few degrees by measuring variations in infrared light from a system 40 light-years away. The fact that JWST can do this at all is a technological triumph that would have seemed like science fiction to astronomers just 20 years ago. Every observation of TRAPPIST-1, even the disappointing ones, represents a genuine leap in humanity's ability to characterize worlds beyond our solar system. There is also a broader implication quietly growing in the background of all this research. TRAPPIST-1 is not alone. Red dwarf stars with rocky planets are everywhere. Whatever rules apply here, whatever mechanisms determine whether a rocky planet around a red dwarf keeps or loses its atmosphere, those rules apply across billions of other systems throughout the Milky Way. Figure out TRAPPIST-1, and you essentially unlock a template that can be applied to a huge fraction of all the rocky planets that exist in the universe. That is the real long game being played here, and it is enormous. So where does all of this leave the search for life in the TRAPPIST-1 system specifically? Honest answer. It leaves it genuinely uncertain in a way that is both frustrating and scientifically thrilling. The simple narrative, 7 Earth-like planets, 3 in the habitable zone, life might be right next door, has given way to something far more nuanced. The system is real, The planets are real, and JWST is producing real data. But reality, as it almost always does, turns out to be messier and more complicated than our initial hopes suggested. What scientists are now trying to determine is whether there is any scenario in which the habitable zone planets maintained enough atmosphere to support surface liquid water despite the hostile stellar environment. They are looking for chemical signatures in atmospheric spectra. They are modeling stellar flare histories. They are calculating how different planetary compositions and interior structures might influence atmospheric survival. This is not a story that is over. It is a story that is just getting genuinely interesting. One thing worth emphasizing, because I think it often gets lost in the headlines, is that the absence of a thick atmosphere does not automatically mean the absence of life. There are organisms on Earth that live in environments that would kill most life forms without hesitation. Extremophiles thrive in boiling acid, in the crushing pressure of deep ocean trenches, inside rocks, in places flooded with ultraviolet radiation. We have to be careful about assuming that Earth's particular biological formula represents the only possible template. If there is subsurface liquid water on any of the TRAPPIST-1 worlds, driven perhaps by tidal heating from the gravitational interactions between the tightly packed planets, then possibilities remain that surface conditions alone do not capture. The conversation about life has not ended. It has just gotten considerably more sophisticated. There is something deeply human about the way we have responded to TRAPPIST-1 from the very beginning. We saw 7 planets, 3 in the habitable zone, and we immediately started dreaming about neighbors. About the possibility that we are not alone in this vast and ancient universe. That impulse is not a weakness. It is what drives exploration. It is what convinces funding bodies to build billion-dollar telescopes and launch them into space. The dream is a feature, not a bug. But the dream also has to evolve as evidence accumulates. And right now, the evidence is telling us to hold our earlier conclusions a little more loosely. JWST still has years of operation ahead of it. Its observations of the TRAPPIST-1 system are ongoing. Every new transit observation, every new thermal emission measurement, every new piece of spectroscopic data is going to add another layer to a picture that is already far richer and more complex than anyone imagined back in 2017. The story is not over. In fact, in many ways, the truly interesting chapter is only just beginning. What we are witnessing right now is science doing exactly what science is supposed to do. Building models, testing them against reality, finding out where they break, and then building better ones. The TRAPPIST-1 system has broken quite a few models already. It will probably break a few more before JWST is done with it. And every time it does, our understanding of planets, of stars, of atmospheres, and of the conditions required for life will sharpen in ways that benefit the entire field of astronomy and the entire human project of understanding our place in the cosmos. I want to leave you with one final thought, because I think it captures something essential about this whole story. We sent the most powerful space telescope ever built to stare at a dim little star 40 light-years away, and what it found did not match what we hoped. The planets are barer than expected. The atmospheres thinner or absent. The odds, at least for some of the worlds, less favorable than the headlines of 2017 suggested. And yet here we are, more fascinated than ever. Because the unexpected is exactly where discovery lives. Every time the universe refuses to behave the way we predicted, it is handing us a gift. A clue that our understanding is incomplete. An invitation to go deeper, look harder, and think more carefully about the fundamental nature of worlds and the conditions that allow life to take hold. TRAPPIST-1 is not the simple story we wanted. It is a far more complex and compelling one. And JWST is just getting started. If you want to see the earlier videos where we broke down the original discovery and the first JWST observations, they are linked right here. And if this video got your brain going the way it got mine going while researching it, the subscribe button is right there, because there is absolutely more of this coming as JWST continues to reveal what our universe actually looks like rather than what we hoped it would be. See you in the next one.